Hello everyone. We are going to discuss about geosynthetic applications. In weak deposits or in weak soils, soil bed or weak ground. You know that what is the problem of weak ground? If there is a weak soil bed and you are going to have the foundation, so you want to have a foundation on weak soil bed. Let's say this is the footing embedded in weak soil deposits. This footing is subjected to static loading or it is subjected to cyclic loading. And if the soil is weak, naturally, this implies that the shearing resistance of the ground is very low. So what will happen if you are going to transfer the load through this footing to the weak soil ground? It's going to fail in shear. So it will lead to shear failure. So this leads to shear failure of soil bed. And therefore, you need to improve the ground. And therefore, we need to improve the ground. So that the shearing strength of the ground or the soil bed is adequate for the loading. The weak ground has got another problem of settlement. The another problem of weak ground or weak soil bed is settlement. Excessive settlement is going to endanger the stability of the structure. So there should not be, the settlement must be under the prescribed limit, allowable limit, permissible limit. So here the problem is we need to improve the ground condition. The weak soil, we mean it could be soft clay, weak soil bed, it could be soft clay bed, or it could be loose granular bed. In both the condition, you will have the load carrying capacity is going to be on the lower side. And therefore, friends, you can apply the geosynthetics. You can think of geosynthetic for improving the ground condition. So here you can use geosynthetics. Geosynthetics or geosynthetic materials. In my last video, I have talked about various types of geosynthetic materials such as geotextile, geogrid, geocells, so many varieties. So those geosynthetic materials can be used for the primary function of improving the shearing resistance of the ground. You have to improve this. You have to take care of this. Therefore, you need reinforcement. If you want to improve the shearing resistance of the ground, the geosynthetic should be used as a reinforcing element, reinforcing material. So we can have either geotextile, we can have geogrid, or there are many other forms, geocells. These are going to improve the soil. My own research input. And if you see the research work being carried out in India at all the premier institutes such as Indian Institute of Science, Bangalore, Indian Institutes at Delhi, Chennai, and elsewhere, shows that geosynthetics can improve the load carrying capacity of a footing. So how to improve the load carrying capacity if I need to have a foundation? It should not fail in shear. There must not be any failure of soil bed. And also the settlement aspect must be looked into. This is also important. No excessive settlement. So friends, the various experimental data that's available in the literature, lot of experimental data that's available in the literature. If you see Planar geosynthetic reinforcement in the weak ground, in the weak soil bed. It's a highly encouraging. The results are highly encouraging. So if you are going to share, put the reinforcement. Say, I put the reinforcement here. I'm going to place the reinforcement. These are planar reinforcement. These are the reinforcing element. But it's planar. So if you reinforce this, lot of literature you will be finding, lot of research input you will find it, that it increases the bearing capacity manifold. My own research input says that you can increase the bearing capacity in weak granular bed. If it is a weak granular bed, you can improve the bearing capacity by 3 times. In soft clay also you can improve the bearing capacity. Work carried out by Hegde Amarnath at Indian Institute of Science, Bangalore, and many other researchers. They have developed so much of database that you can carry out the regression analysis. And regression analysis have been carried out. Equation for bearing capacity have been developed for the reinforced bed. So let's talk about the reinforced bed. The various parameters that affect the performance of this footing. So various parameters that affect or affecting the performance of the footing are: number one, this reinforcing element that you have put it. These are the 3 layers. 1, 2, 3. These are all planar geosynthetics. These are all planar geosynthetics. That means it could be geogrid. Geogrid has got high tensile strength. Soil is weak in tension. So you need to have a geosynthetic which has got high tensile strength. You can use geotextiles as a reinforcing element. Reinforcing layer. So what are the various parameters affecting the performance of the footing? One is type of the geosynthetic and tensile strength of geosynthetic material. This is important. What type? Is it planar or it is cellular? Cellular, three-dimensional, 3D. Like, for example, geocells. It's like this. Geocells interconnecting. So many geocells interconnecting, and you can put it in the soil. You can have infill material here. Infill material. That is soil. Maybe granular. Or maybe fine soil. That is the infill material. So either you can have planar geosynthetics, such as geogrid, geotextile, as the reinforcing layer, as shown in this diagram, or you can have 3D cellular materials such as geocells. I've already explained you what is geocell. And a lot of experimental data are available. Very recently, lot of research work have been carried out at premier institutions and in the research laboratory of India and elsewhere in the world. And they have got very encouraging result. There is lot of improvement in load carrying capacity and considerable reduction in the settlement of the footing. So one thing is, what is the type and tensile strength of geosynthetic material? Depending upon the polymers from which it has been manufactured, that also plays an important role so far as tensile strength is concerned. Then what is important is, what is the depth of this reinforcing layer? So that's also important. Or depth of reinforced zone. So second important parameter is depth of reinforced zone. What is the depth of reinforced zone in this figure? This is the depth below the base of the footing up to the bottommost. This is called depth of reinforced zone. Depth of reinforced zone. What is the width of this reinforcement? That's also important. What is the vertical spacing between the reinforcement? That's also important. So then, the another important parameter that affects the performance of your footing is the vertical spacing, delta V. between two consecutive reinforcing layer. What is this depth? This is also important. Below the base of the footing, at what depth you have placed the first reinforcement of geosynthetics. So this is also important. Let's say this is delta V1. This is delta V. The vertical spacing. The width of the reinforcement. B for the reinforcement R. This is also important. B is the width of the footing and D is the depth of the footing, dx. So friends, what is important is your delta V, delta V1. What is delta V? Vertical spacing between two consecutive reinforcing layers. What is delta V1? First layer, vertical spacing between the base of the footing and first reinforcement of geosynthetics. I'm talking about planar geosynthetics. That's important. And then what is important is also the form of reinforcement. What form it is? Is it planar? It is cellular? What kind? That's very important. So these are then what is the depth of reinforcement is equally important. Because when you apply the static loading, how deep the pressure bulb is going? What is the zone of influence? The zone in which the load is felt. So pressure bulb. We have learnt about this in geotechnical engineering by applying Bouwsnik or Westergaard's theory for stress distribution. We know what is the variation of vertical pressure or shear due to the loading. Let's look to that. Let's find out how the pressure is going to be. how the pressure, if you have the loading, embedded into the ground, at any depth Z, you can find out for the surface loading. Similarly, for this footing, the intensity of load, intensity of loading, let's say the load is capital Q, that gets spread over the area of the footing. This is the intensity of the loading. Capital Q, the static load divided by area of the footing. The vertical pressure is going to be maximum at the center. So let's say the center line, I can draw it. This is the center line. And how the vertical pressure is going to change. It's going to change maximum here and then gradually it's going to decrease. Same thing on this side. This is the locus of vertical stress. Vertical stress. It is maximum here at the center of the footing. But if you want to have the shearing, the shear, how it is going to change? It keeps on increasing and it becomes maximum, then it decreases as you go away. So this is the maximum. So the locus of this for shear, variation of shear stress, tau. Similarly on this side. Like this. So if you join, this is the maximum. Maximum shear point. Maximum shear point somewhere here. Near the corner. If you go to the another layer and plot it, the shear. So maximum somewhere here. And if you join, this is the locus of maximum shear stress. And if the ground is weak, it will fail. The maxima. So this for shear stress, variation. Along the horizontal plane, it is going to be maximum somewhere here. So what is going to happen? The soil will fail if it is weak. And if the soil is going to get sheared, then it will move like this. And therefore, below the footing, you have seen the soil moves like this. It fails and then it moves. Soil movement is going to be like this. So friends, if the soil is going to fail in shear, then it is a catastrophic situation. The ground is going to give in and your whole structure will collapse. But if you have geosynthetics, which has got high tensile strength and there is sufficient bonding between this planar geosynthetics and the adjoining soil, then this shear is going to have a tension failure. Soil is weak in tension. But if I am having the geosynthetics, which has got high tensile strength, it will not fail. The ground is not going to fail. So my geosynthetics is going to bend here. If I have a layer of geosynthetics here, this is the zone. This geosynthetic here, how it is going to bend then? How it is going to behave? This geosynthetic will bend like this. This is the geosynthetic that is going to bend like this. Because the shearing is going to bend it, and therefore a tension will get developed here. Right? It's going to be like this. So, because of this tension, now I have the geosynthetic which can resist the tension. So there is no scope of failure. And the ground will be quite healthy. And therefore, in layers, I can go it. But how deep? What should be this dr? What should be this dr? How deep? I should put the reinforcement. How many layers? What should be this? The width of the reinforcing layer vis-a-vis to the width of the footing. What should be the vertical spacing? What should be this delta V1? Are all matter of research. And I'm happy to inform you that there are a lot of research papers. So in my next video, I will talk about what are the research papers. My own, I've got so many, my own PhD work. I have done it. And I found that the bearing capacity improves by 300% in weak granular deposit. Even in weak cohesive ground, soft soil, geocell, three-dimensional cellular geosynthetic material works wonders because of the confining effect. And therefore, you can improve the ground condition. So, ground condition can be improved upon substantially. Reduction in settlement will be substantial. That will reflect in your next video. Please look for the next video for the quantification of improvement in bedding capacity or load carrying capacity of the footing based on the research work, based on the available data, and also the reduction in settlements. What is the role of this infilling material? Everything I will discuss. So friends, thank you very much and hope it was interesting to all of you.